Hello everyone, my name is Bernardino Realino M. My name is 131200016, and today I will be presenting to you a topic on electrical propulsion, which is known as a rapidly advancing area in rocket and spacecraft propulsion technology. Now, for the overview of electrical propulsion system, what is it? Electrical propulsion refers to any propulsion system that utilizes electrical energy to accelerate its propellant and to accelerate a propellant and produce the rocket's thrust. Now, unlike a chemical rockets, electrical propulsion system do not rely on combustion. Instead, they use electrical fields, magnetic fields, or heat generated from electricity to produce high-speed exhaust. Now, one of the key advantages is the very high exhaust velocity, as we'll discuss later on in the presentation, which translates into a high specific impulse. And as mentioned in the as mentioned in the book Rocket and Spacecraft Propulsion, written by Martin in 2005, electrical propulsion is becoming essential for long duration space missions and is now a key for to enable a deep space exploration like the ones seen in the movies. Now, the basic principles of the propulsion. Electrical systems generally follow a simple principle, which is electrical power is used to accelerate a propellant, usually a noble gas like xenon, to extremely high velocities. The energy source for this is typically solar panels or nuclear power systems, depending on the mission. This high exhaust velocity results in a very high specific impulse, which means much less propellant is needed to achieve the same changes in velocity compared to chemical rockets. However, the thrust is usually quite low, so the system may not operate in the same level as a chemical rocket. So um, it to be able to actually survive a long distance mission, a long duration mission, it needs to slowly build up its speed, which is also at the same time perfect for deep space mission or satellite station keeping. And next we have the types of electrical thrusters. So we have three: electrothermal thrusters, electrostatic thrusters, and electromagnetic thrusters. So first is the electrothermal thrusters. What is it? For example, it is a resistor jets and arc jets. It heats the propellant using electricity before expanding it through the nozzle. They offer moderate performance with ISP typically around ranging from 300 to 900 seconds. On the second one, we have electrostatic thrusters. It normally operates like a gridded iron engines, where the system utilize electric fields to accelerate positively charged ions. They usually have a very high ISP, ranging from 2,000 to 5,000 seconds, but sadly they deliver very low thrust. Lastly, we have electromagnetic thrusters. To name a few examples, Hall effect thrusters and magnetoplastic dynamic thrusters. Now, this use what we call a Lorentz force and plasma dynamics to accelerate propellants, offering a balance between performance and thrust, and widely used today specifically for the Hall thrusters. Now, the first one we have ion thrusters, which is the electrostatic one. Now, when we take a closer look at this ion thrusters, it operates by ionizing xenon gas and accelerating the ions through charge grids using strong electric fields. The positive ions are expelled at very high speeds, sometimes over 40 kilometers per second, yeah. And the neutralizer, it separates the cathode emitted by wait. So for the neutralizer, it releases electrons to balance the ion beams, preventing the spacecraft from charging up and its performance. This system is proven to be highly effective. For to use it as an example is the NASA's Deep Space One and Dawn missions. Both use ion engines to reach distant asteroids using only small amount of xenon. These and this engines usually operates at low thrust levels, typically just a few millinewtons, but over time they can deliver enormous velocity changes. Next, we have the Hall effect thrusters, which is the electromagnetic. Now, the example can be seen in the image below the title. This is the gleaming white light right there. Now, the Hall effect thrusters work differently from the others. In the system, the magnetic field is applied perpendicular into the electric field inside the cylindrical channel, where the electrons are trapped in a circular motion, also known as the Hall current. It ionizes and become the incoming propellant. Now, these ions are then accelerated out of the thrusters by the actual electric field, which ultimately produces thrust. Now, these devices are also are much simpler than ion thrusters because they do not use physical grids. As a result, they're more robust and can operate for longer durations. For this electromagnetic thrusters, it usually has an ISP that ranges from 1,000 to 3,000 seconds, with the thrust levels that can reach up to a few newton depending on the power input. Next, we have the performance and the equations. So we also have four here: thrust, specific impulse, energy relation, and finally we have electrical efficiency. Now the thrust for the general equation is it governs by the Newton's second law, force equals mv, uh, mass flow mass flow rate times the exhaust velocity. That is F equals m dot multiplied by VE. However, for the electrical systems, it is kind of different because as you can see, the equation is actually F, which is approximately equals to 2 Pn multiplied by efficiency divided by VE. That is what's it called? The Pn is basically the input power, electrical input power, and N is as we said, is the efficiency. Now, because the exhaust velocity is so high, the thrust ends up being very small for a given amount of power. But this is a trade-off we accept in exchange for excellent fuel efficiency. Now, the classic, how do I say that? How do I say it? The Sokolovsky equation, where delta V equals the VE multiplied by the natural log of MO, initial mass, over final mass, which is similar to the rocket equation, and it's still applied. But the key takeaway is that here is that the higher VE gives the higher delta V for the same amount of fuel. Okay, next we have the disadvantage and advantages and disadvantages. So from each side we have three. For the advantages, we have very ISP, efficiency, it's very efficient, and it has a precisional thrust. Um, Electrical propulsion offers a very high specific impulse, which means there is less fuel is needed, making it much more cost effective. Now, it is also has a precise control of thrust, which is ideal for satellite positioning, and is well suited for long duration missions that needed gradual but sustained acceleration. Now, on the other side, we have the disadvantage. Now, for this, the thrust is very low, power hungry, and complexity cost. I know we've said it is efficient because of the lower propellant mass required, but it actually is, what's it called? It contradicts itself because there's a high technological risk and control systems. Um, has low thrust, which means you cannot launch from the surface. Um, it cannot be launched from the surface or fast maneuvers. and long burning times needed to change the velocity. It is also power hungry, which requires a large solar arrays, and each reactor produces kilowatt to megawatts of power. Now for its real-world applications. So we have, for example, satellite station keeping. For the satellite station keeping, the geostatic comsats routinely use Hall thrusters for ion engines to maintain position with minimal propellant. For the next one, we also have deep space mission, like I said, um, very high ISP, and it's efficient and precision control, which is also suited for deep space missions used by NASA on NASA's Dawn missions, and ESA's Smart 1 lunar orbiter uses ion drivers upcoming Psych asteroid missions that will use Hall thrusters. Now we also have the third example is the orbit raising. Commercial satellites now use electrical for initial orbit raising. For example, via electrical buses like Starlink uses Hall thrusters. Now for the robotic probes is also a real-world application of electrical propulsion, where near all probes like BP Colombo and Hayabusa 2 include some electrical thrusters for propulsion or station keeping. And now we have the comparison for electric thrusters. So we have ion gridded, thruster type ion gridded, Hall effect, MPD, and uh, Fasmir. Now each of these thruster type has different principles. The first one is electrostatic acceleration of motions. Hall effect has E times B drift plasma discharge. MPD is Lorentz force with a arc discharge. And Vasimer is RF plasma with magnetic nozzle. Now, ion engines usually have a very high ISP, which can reach, as we discussed before, 5,000 seconds, but produces only a few millonewtons of thrust. Now, for the Hall effect from the Hall thrusters, it provides more thrust, up to a few newtons, with ISP ranging from 1,000 to 3,000 seconds. For the last two, MPD and VAS-IMR thrusters, it's currently very experimental, but they show a promise for high power, high thrust for deep space missions, especially if nuclear power becomes an option. So that's it for the presentation. Thank you for listening.